All right, so you're probably noticing a theme here on A, B, and C. The graphs are looking, they have a lot in common, but we're kind of tweaking them as we go. And again, our perspective here is we're trying to not only figure if we have max or mins, but essentially under what circumstances will we have both a max and a min, and if so, what would be the possible locations of those max and mins, okay? So on example D, here we are, it's kind of the same as example C. The only difference is we're redefining the value at 0 to be something different. So in this case, if you'd like, I'll just copy and paste. Let's see if it still held it in the memory over lunch. Nope. Oh, I copied something else. Yeah. All right. So come back up here, or redraw it again if you really just like drawing parabolas. Who doesn't, right? All right. So we do have a closed interval from -1 to 2, so the endpoints are good. But once again, at 0, we're defining it to be a different value. So open that up. And then come back and then put a dot at the origin. All right, so this function is still defined everywhere on the interval, but we have what type of discontinuity at 0? Is that a jump or a hole? It's a hole, right? Because the limit exists, right? Remember, the jump is when the two one-sided limits don't exist. Okay, do we have a maximum? F has a ... Yeah, we have a maximum again. Of same thing, y equals 5 at x equals 2. Sweet. Do we have a minimum value? Is there a y value on this graph, on this closed interval, such that there are no y values lower than it? Yeah, right there, 0. So we do have a minimum of y equals 0 at x equals 0. What's the value of the derivative at the right endpoint? Does not exist. What's the value of the derivative at the vertex or at x equals 0? Also does not exist, right? If it's not continuous, it's not differentiable. Okay, so far, every time we've had a max or min existing, it's either been at an endpoint or at a place where the derivative was either what or what? 0 or d and e, right? Okay, that's interesting. Okay, so we're done with that one. Let's look at this one, sine of x. Sahala, right? From 0 to 4 pi. How many cycles is that? 2, yeah. So let's go ahead and sketch the graph. And remember how we did that? We'll bisect it and we'll call that 2 pi. We'll come out here and call that 4 pi. So to get our critical values, we'll bisect 2 pi to get pi. We bisect it to get pi halves, bless you. And now we have our quarter cycle counting interval. So that's easy then to create the others. We're counting by pi halves, so 3 pi halves, 4 pi halves, 5 pi halves, 6 pi halves, 7 pi halves, 8 pi halves, so on and so forth. The amplitude is what? The distance between high and low is 2. The amplitude is 1, right? So it's just a plain old Sahala. So Sahala is axis, right? So axis high, axis low, axis. And then we go for the second cycle. Boom, there it is. So then we connect it with little lines. There we go. Okay. So we sketched real quickly the graph of sine or Sahala for 2 cycles from 0 to 4 pi. On that closed interval, it is closed interval, right? So the endpoints are in play. Do we have a maximum value? We have a maximum of, what'd you say, pi halves? 1. Very good, very good. We have a maximum of y equals 1 at x equals pi halves. Is that it? And 5 pi halves. Good. Now, does that mean that we have 2 maximums? I thought because it was an absolute maximum or a global maximum that there could only be 1 maximum value. Do we still just have 1 maximum value? Absolutely. It just occurs at 2 different places, right? Because the maximum value is 1. That's like saying the high temperature for the day was, 55 degrees, and we reached that temperature at, 11 a.m. and 6:42, right? you can have that maximum value occurring at more than one time, but still just the one maximum value. Okay, cool. Similarly, do we have a minimum value? Yeah, the cat's out of the bag on this one. We have a minimum value of y equals -1 at x equals 3 pi halves, and I'll just put a comma there. How about 3 pi halves comma 7 pi halves? Is that an okay way to list them if there's more than one? Yeah. Okay, so this example is not just to review Sahala, but to illustrate that, yeah, you can have maximum values occurring at more than one location, but there can only be, if any, one value. Okay, how about this fella? 2 minus 3x, we have a closed interval. What can you tell me about the graph of this guy just looking at the equation? It's linear, right? The y-intercept is 2, and the slope is down 3, right 1, so something like that. We'll just connect the lines like that. Boom. All right. That's a good enough sketch, right? Now, to look at the interval in question, we got -1, so we'll kind of go up, put a solid dot, and then 2, looks like it's going to be down here, negative land, solid dot. So I'll just highlight the interval. We're looking at this interval here. The line goes on forever and ever. Do we have a maximum? No maximum? Yeah, I think we do, right? Because remember, we're looking on the closed interval here. So we do have a maximum value. It looks like it's at the left endpoint. It's going to be, what's the value if you plug in a -1? 5? Y equals 5, max of, at x equals -1. So that's another endpoint. What's the value of the derivative there on the closed interval? dne, right? dne. Do we have a minimum? Yep, we have a minimum of y equals, is it -4? Yeah, -4 at x equals 2. So here's another instance where we have both a max and a min. What can you tell? Oops, there's one more. Sorry. Any questions on that one? Do we have any values on here where the derivative was 0? Where the graph turned around vertically? No, but yet we still have a max and a min. It just occurred at the endpoint. Okay. The next one is kind of the exceptional case, and this is the one that's going to refer back to that original definition where I told you the equal sign kind of comes into play, right? F of x equals 3. We have a closed interval. Let's go ahead and sketch the graph. What does f of x equals 3 look like? Horizontal line. Very good. Y equals 3. So the domain is all real numbers, but we're only looking at it from -2 to 4 over here. So let me highlight that region, or just trace over it. All right. The values along that line segment anywhere and everywhere are 3. Yay, go us. Does this function have a max? Yeah, if you think about it as, does this thing have a highest value? Intuition might say, no, there is no highest value, right? Same thing, does this graph have a lowest value? I don't know. They're all the same, right? But if you go back to the definition with the equal sign and you just rephrase it the other way, is there a y value on this closed interval such that there is no other y value bigger than it? Yes, there is no y value on this interval bigger than what? 3. And by that definition, then, f has a maximum of y equals 3. Okay? Where does it occur? On the interval from -2 to 4. So you could say for all x on the closed interval from -2 to 4. Everywhere. So it occurs definitely more than once. It occurs infinitely many times. That is an absolute maximum value. All right, so if it's a maximum, I guess it can't be a minimum, right? It definitely could be. Yeah, it's the same argument. Is there a y value on this interval such that there is no y value smaller than it? Yeah, same thing. We have a minimum of y equals 3 for all x on the closed interval from -2 to 4. So this is kind of like the exceptional case. It's kind of the boring case. Maybe we even call it the trivial case, right? Where you have both a maximum and a minimum value being the same because you're on a horizontal line segment, okay? And so that's why we need that equal sign there to kind of take care of that, right? Okay, what can you tell me now about not every one of these functions was continuous, okay? We had a lot of discontinuities. But for every single one of these, what was the common characteristic for all of the ones that had max and mins? Was there a common characteristic? Let's see, this one we had endpoints. We had both the max and min. This one wasn't, so that one's out. This one didn't, it was out. This one did, but it was kind of interesting, right? We already saw where this one could potentially not, right? In the previous example, it's just a matter of where is it defined at 0. So this one wouldn't be, this situation here would not be guaranteed every time. We just kind of got lucky. But this one did, right? That one did. This one did. And this one did. So aside from this oddball that kind of by luck, you could say, had both the max and the min because of where we defined the function at 0, what do all of the other ones, that one, take a good look, that one, and this one, what do they all have in common? They're continuous on what type of interval? They were all closed interval. That was pretty much what they all had in common, right? They were continuous on the closed interval. And every single one of those guys had both a max and a min. Okay? Good. That's important. What then were the possible values of x where the max and mins occurred? This one occurred at the endpoints, right, for sure. But it also occurred everywhere on the interior. What's the value of the derivative everywhere on the interior? 0, 0, 0. Okay. What about this fella? This guy occurred at the endpoints, where the derivative is undefined. This guy occurred at not the endpoints, but on the interior. What's the value of the derivative at each and every one of those places? 0, horizontal tangent lines. And this guy over here, we already talked about. This one had one at an endpoint, where the derivative is 0, and one at a place where the derivative is 0. So let's see if we can summarize that. When it was continuous on the closed interval, f had both a max and a min. And then we could say they occurred at one of two places, at either what? An endpoint, good. Not an endpoint, an endpoint, where f prime equals d and e. Yeah, good. Or a horizontal tangent, where f prime equals 0. We kind of discovered that. It's a small sample space, but is it enough to maybe think that it might continue? Yeah, I think so. Okay. Well, it's true. It's summarized in this theorem. Okay. This is our second VT theorem of the year, right? This one is called the extreme value theorem, or the EVT for short. The other one we had was the what? IVT. Yeah. The IVT said if a function is continuous on a closed, then we're going to pass through all the y values in between the endpoints, and there's an x value to generate it. The EVT is called the extreme value theorem. And here's what it says. If f is continuous on a closed interval. That sounds real familiar, doesn't it? That's what we just came up with here as the prerequisite necessary condition to have both the max and min. It's also the same hypothesis as the IVT. So it says if the function is continuous on the closed interval, then get this. You hit the nail right on the head, guys. Then f has both a maximum value and the minimum value, where? On the closed interval. You were right. If the function was continuous on the closed, we're guaranteed to have both a max and a min. Could it occur more than once? Yes. Could it actually be the same value? Yeah, in that weird horizontal case. Good. And notice this theorem doesn't really tell you where they occur. It's just an existence theorem. Hey, continuous on a close? Yeah, you're going to have both the max and the min. Find them, good luck. I can't tell you that. All right? So, without looking, what does the EBT say? If what? Continuous on a close. Yeah. Then what? What'd you say? Local max, local min. Have we talked about that yet? We kind of addressed it with King of the Mountain when you zoomed in, but no, we're not talking about local right now. We're talking about max mins, also known as what? What are the other qualifiers we could throw in front? Absolute or global, right? Either one of those. So if you want to add them for emphasis, right, you can. Global maximum, absolute maximum. But you don't have to say that. You could just say max, you could just say min. Okay, we'll talk about local extrema. That's a little bit different. Okay, so here's some examples on a closed interval where the EBT applies. There's your purple graph from A to B, right? Continuous on the closed interval. We have an absolute max. It occurs at f of c. And we have an absolute min. It occurs at f of d. See that? What's the value of the derivative at both places? 0. So that's trending. Hey, let's look at the EBT real quick, right? Because it's the same if part. If it's continuous on the close. Remember, here's on the IBT, not the EBT. If you draw horizontal lines between the endpoints, remember the EBT says then, as you get from that point on the left to this point on the right, you're guaranteed what? To pass through every y value in between them, right? At least once. You can't get from that blue line to the bottom blue line without passing through all the vertical space in between, okay? Why did the chicken cross the road? He had to. He couldn't teleport. Good. All right, so that's just to review the IBT. Okay, cool. Here's another one. Continuous on the closed interval from A to B. What's the local max? I'm sorry, now you got me saying it. What's the maximum? F of C, not C. F of C, right? What's the absolute minimum? F of B, okay? So again, we have a derivative at 0, and then we have an endpoint where the derivative is undefined. And then this guy, of course, continuous on the close. What's the maximum value? Yeah, f of c and f of b, the same value. And the absolute minimum is f of d. And again, the value of the derivative there is undefined. What about this? I didn't have this one drawn here, but what if I have this? Here's A. I have that there. We'll call this C. Does the EBT apply to this function from A to B? Is this function continuous on the closed interval? Yeah, it's connected, right? Is it smoothly connected? Is it differentiable? No. Does it have to be differentiable for the E or the IBT? No. So, by the EBT, there should be both the absolute and global max min. What is the absolute maximum? F of C. What's the value of the derivative at F of C? dne at C. Yeah, it's dne, right? What's the absolute min? Not B. F of B, and it occurs at B. What was the maximum temperature yesterday? 5 o'clock. What? Yeah. Oh, I'm sorry. I get my X's and Y's backwards. It was 57 degrees. It occurred at 5 o'clock, right? Same thing. Same thing. Okay? All right, so that would still hold true, right? A derivative can be 0 or undefined on the interior. Okay, example 3. Determine if the EBT applies for each of the following functions on the closed interval. If so, find the extrema. If not, explicitly state why. Okay, that doesn't mean using curse words. So here we go. We're going from 0 to 2. Does the EBT apply to this function on this interval? Yes or no? Yes. Well, from 0 to 2, it's continuous on the closed interval from 0 to 2. I spy a discontinuity at x equals what? 1. What type is it? This is jump. Now, the EBT would apply on the interval from 1 to 2, right? On 1 to 2. Would the EVT apply on the interval from 0 to 1? Sorry. It would not apply on the interval from 0 to 1 because it's an open circle. But from 0 to 2, no. Okay? No, comma, EVT does not apply because, why? F is not continuous. You could say at x equals 1, and then should we stop there? Why is 1 relevant? Because epsilon, right, it's on the closed interval from 0 to 2. So that's how you're going to want to answer it mathematically. Here's where we have a discontinuity, which is relevant because that is in the closed interval where it's supposed to be continuous. All right? If it was not continuous at x equals 5, who cares, right? There you go. You don't have to state what type it is, but it is a jump. Okay, letter B. On the interval from 0 to 2, does the EVT apply? No, it doesn't. No, it doesn't. No. EVT does not apply. And then because what? F is not continuous at x equals what? 2. That's enough, right? It's neither continuous at 0, but it's just enough that it's at 2. Either one. Both endpoints are out. Now, just because the EVT does not apply, does that mean that a function then cannot have both a max and a min? Or is it possible for the EVT to not apply and still have a max and min? Yeah, we already saw that, right, on our previous example. Does this one have either a max or a min? No. No min. There's a hole in the bottom. Any max going up to infinity? No. Did this one over here have a max and a min, even though the EVT didn't apply? Did it have a min? It had a min of 0 at 2. Did it have a max? No. What if these open and closed circles were switched? Would it then have a max? Yeah, and a min, right? So just because the EVT does not apply doesn't mean we still can't have a max and a min. The EVT just tells us the conditions in which we are what? Guaranteed, as Justin Wilson used to say. You remember Justin Wilson, the Cajun guy? Yeah? Y'all probably don't know who Justin Wilson was. Okay. Letter C. EVT apply, yes or no? I'm getting the theme here. No, since F is not continuous. Where? In France? At x equals 1, which is relevant because that is in the closed interval from 0 to 2. Okay, what type of discontinuity is that one? Also a jump. Does this function happen to have a minimum value? It does. It's f of 0, whatever that y-intercept is. Does it happen to have a maximum value? Yes, it's 3, I guess, at 2. So here's that example, right? EVT doesn't apply, but yet still had both a max and a min, right? And finally, letter D. EVT apply, yes or no? God, these are all no, right? Because, or since, f is not continuous at x equals what? 0, you could put 0, 2, which are in the closed interval from 0 to 2. One of them is enough to make it not apply, right? Does it happen to have a maximum? It's 3. What's the value of the derivative there? It's supposed to be a cusp. Yeah, D and E, with a little safety tip on it. And it has a minimum also of whatever this value is. And what's the value of the derivative there? 0. Okay. So another example of where the EVT did not apply, but yet still had a max and min. Okay, so every time we've had a max and min, whether the EVT applied or not, it's either been at an endpoint where the derivative is undefined, or at the interior where the derivative was 0 or undefined, right? That's it. Those have been the only 2 places. That's kind of cool. Okay, so let's go ahead and define one thing and we'll call it a day, all right? Definition. Okay? Critical value. It's a definition. So we're not just using critical like in the sense of, man, I need some caffeine. It's getting critical, right? Or I need my Juul, man. Class was too long. It's getting critical. This is a term, right? A definition. A critical value, which I will abbreviate CV. All right? A critical value of a function f, first of all, is an x value. Okay? It has to be in the domain of the function. Function doesn't have to be defined, continuous there, but it does have to be defined. Okay? Doesn't have to be continuous there, but it does have to be defined. It has to be in the domain of the function, such that one of these two things happens. Either the derivative there equals 0, or the derivative there equals dne. Okay? If you include the y value with it, you get what's called the critical point. We now have a way to refer to all of those locations where we just had all our absolute max and mins, right? We were saying, oh, it was a place where the derivative was either 0 or undefined. We can now call those x values what? Critical values, okay? And endpoints are very special critical values because they're on the end. We have critical values on the interior as well that we've seen. So a critical value is any value where the derivative is 0 or undefined, correct? Not quite. Not any value. Any value in the domain, right? Any value in the domain where the derivative is 0 or undefined. Could you call this vertical asymptote right here at 2? Could you call 2 a critical value? If there's a vertical asymptote there? No! Is it in the domain? No. So it's an interesting value, but is it a critical value? No. What about 0? No, not a critical value. It has to be in the domain. All right, have a great day.